Okay, so I know we've done a few examples that have involved friction so far, but this one's going to be the first real look that we've had back with friction. Okay, so example 2.4.1 says you are trying to move a 45 kilogram crate. You can exert a force of 360 newtons and can either push or pull at an angle of 25 degrees. The coefficient of kinetic friction between the floor and the crate is 0.36. Is it faster to push or pull the crate? So the big thing we need to answer is really this question here, is it faster? And think about what that's asking us. In terms of what we're looking at here, we're looking at forces, right? So we're going to have to determine which one gives us the greater F net, which is in turn going to give us the greater acceleration, which would be less time to either push or pull the crate. Okay, and that's really what we're going to try to solve for, is the acceleration of each of these scenarios. Okay, so first let's look at what it would look like to push the crate. So if we have push, okay, and on our floor, that should be flat, we have a 45 kilogram crate. And in both instances, I'm assuming that the person is taller than the crate. Okay, so what that means is when I'm pushing, my arms, oh, sorry, that is a little bit far. Let's redraw this guy. So that means when I'm pushing, my arms here are creating a 25-degree angle with the horizontal. Okay, so if we go and look at drawing the free body diagram for that situation, okay, again, I'm going to take the crate, that is 45 kilograms, okay, and let's look at the forces that we know are acting on it. Okay, well, it's on a flat horizontal surface, okay, and with any object, we know we have that force of gravity that acts down, okay, and there's going to be some force of normal in this case that's acting up, okay. I can't say that they're equal in this situation, and I'm going to show you why here in a second. Okay, so we are pushing at an angle of 25 degrees, and it's almost like it's below the horizontal, right? Notice you're applying the force in this direction. So if I translate it over to the right side of the force, or of the crate, that means my applied force is here at an angle of 25 degrees. Okay, and then we know we have some force of kinetic friction that's acting back in this direction. Okay, so this is what your free body diagram is going to look like for this situation. Notice what we're going to be able to do is we have to break down our applied force into an X and a Y component. And if you look at the applied force in the Y direction, notice the applied force in the Y direction is acting down. Same direction as gravity. So our normal in this case, for it not to accelerate through the floor, right, for F net to equal 0 in our Y direction, our normal is going to have to cancel these two forces. And that's why I couldn't say that the force of normal was equal to the force of gravity in this case, because my applied force actually adds to the force of gravity, which means the floor actually has to exert more force back up onto the crate in order for F net to still equal 0 in that direction. Okay, so the big thing that we're going to have to solve for in the Y direction is Fn. Because if you remember, all they've given us here is the coefficient of kinetic friction is 0.36. in order to actually be able to solve for what that force of kinetic friction is, remember, Fk is equal to mu k times Fn. Last year, a lot of the time, we were able to say that Fn equaled Fg because we didn't have another force that was acting in the y direction. This year, that may not be true. So we're going to have to use the y direction to solve for Fn, so then we can then plug that into the x direction and determine that force of kinetic friction, and therefore what that F net in the x direction is. Okay, and that's really the strategy we're going to employ here for both the push and the pull. But let's just start with the push. Okay, so let's look at the y direction first. We're always going to start with that y direction in this case when we're on a flat horizontal surface, because we know that F net in the y direction is 0. Right? There's no acceleration in that direction. You're not pushing it through the floor. It's not floating off the floor, so F net is 0. Okay, and then let's look at the forces that act in the y direction. Okay, we're going to do normal convention here. I'm going to do up as positive, and I'll do right as positive in this case as well. Okay, so my forces that act up are the force of normal. Okay, and we're subtracting both the force of gravity that acts down and that applied force in the y direction. So what that means is the normal force, like I said, is actually equal to the force of gravity plus that applied force in the y direction. Because you're pushing a little bit more into the floor to actually move this crate, so the floor has to work harder as to not accelerate the crate through the floor. Okay, so now let's go and solve for Fn. So Fg is just mass times gravity, where the applied force in the y direction is the magnitude of that applied force, times, in this case, notice y is opposite that angle, so we're using sine theta. Okay, so we get 45 kilograms multiplied by 9.8 meters per second squared, plus our applied force, which was 360 newtons, multiplied by the sine of our angle, which was 25 degrees. Okay, and when we plug these values into our calculator, I get 441 newtons for the force of gravity, and then 360 times the sine of 25 gives me 152.14 newtons. Okay, I'm going to just carry those extra 2 decimal places because you'll see our sig figs are 2. This already has 5 there, so I think that's more than enough. Okay, so when we add that to 441, we get that F net, or sorry, the force of normal, not F net, the force of normal is going to equal 593.14 newtons in that up direction. Okay. Now, remember, the reason we go and solve for this Fn, or the force of normal, is because we need it for the x direction. Okay, so now we're going to go and look at the x direction here. And the F net in this case is not equal to 0. Okay, we're trying to solve for what that acceleration is in this direction. So let's simply look at the forces that act in this direction. Well, in the x direction, we have the applied force in the x direction that's going to accelerate it forward. Then we have that force of kinetic friction that's acting against it. So I'm subtracting it. Okay, remember, F net is just equal to a mass times an acceleration. Okay, our applied force in the x direction is Fa times the cos of theta now, because it is adjacent. And remember what force of kinetic friction is. Force of kinetic friction is that coefficient mu k times the force of normal. And that's why we needed to solve for this in the y direction, because we're going to plug it in here to solve for what that force of kinetic friction is. Okay, so I'm just going to leave the mass times acceleration on the left side of the equation for right now, and let's solve for what the actual F net is. Okay, so we get 360 newtons times the cos of 25 degrees, subtract our coefficient, which is 0.36, times our force of normal that we just solved for, 593.14 newtons. Okay, so let's go and simplify here. Cos of 25 times 360 gives me 326.27 newtons, minus 0.36, which is our coefficient, times that normal, which is 593.14, and I get 213.53 newtons. Okay. So when I go and subtract these again from each other, I get the F net in the x direction is equal to 112.74 newtons. Okay, so this is what our F net in that x direction is. Now we know what the F net is. Let's go and get the acceleration. So the acceleration is just going to be equal to that net force that we just solved for in the x direction divided by the mass of the object. So 112.74 newtons divided by 45 kilograms gives us an acceleration of, I get 2.5053 meters per second squared. Okay, now that's the push. Now we're going to employ the exact same strategy with the pull and then compare the accelerations in the end. Okay, so now that we've solved for the acceleration for pushing, we're going to do the exact same for pulling. Okay, you may think that oh my gosh, we're only halfway done, but you've actually done a lot of the calculations already. So you're going to be able to just carry values forward that you did above down below here. Okay, but we're going to redraw the scenario again. Okay, now we have a 45 kilogram crate. Okay, and this time we're looking at pulling that crate, where again our arms create that 25-degree angle. Okay, so we're pulling in this direction, so therefore your applied force is acting up like this. Okay, so now when we go and redraw our free body diagram, okay, a lot like the last situation, we know we're going to have the force of gravity that acts down. Okay, again, you're going to have that force of normal that acts up because we're on a horizontal surface. Okay, I'm going to draw that horizontal again. And now this time, instead of that applied force going down, notice it's going up at an angle of 25 degrees. Okay, and we still have that force of kinetic friction that acts back. Okay, so notice it's pretty much the exact same. The only difference is this applied force has now been flipped. Okay, but if we break it down into its components again, you know you're going to have some x component that acts forward. Okay, and you also know you're going to have some y component, but this time it acts up rather than down. Okay, so really the only change to this scenario is when we look at the y direction. Okay, F net is still 0 in the y direction. Only difference now is if you look at your forces, Fn, or the force of normal, and the applied force in the y direction both act up, where force of gravity acts down. So that becomes the only one I subtract when I add those other two forces. So now when we go and solve for the force of normal is actually going to be the force of gravity subtract that applied force in the y direction. And if you think about it logically, that makes sense, right? We have some applied force that's acting up. So we're lifting off the ground, not like fully, but enough that the ground doesn't have to work as hard to counteract gravity, because we're doing some of that work for it by that applied force going in this y direction up. Okay? So now, to solve for the force normal, notice we're not going to have to do any of those calculations anymore because you've already solved for all these forces, right? Force of gravity was 441 newtons, and your force applied in the y direction was 152.14 newtons. So this time, when we are pulling, the force of normal is only equal to 288.86 newtons, okay? Now think about doing the exact same thing in the x direction again. Okay, we're looking for F net in the x direction. F net in the x direction, there's no change to that. It's still just the applied force in the x direction minus that force of kinetic friction. Okay, but remember, the way we solve for the force of kinetic friction is you're taking that coefficient times this force of normal. Okay, so although I don't have to solve for that x component again, okay, so the x component was 326.27, we are going to have to calculate what that new force of friction is. So I take 0.36, and this time we're multiplying by 288.86 newtons. Okay, so we still have 326.27 newtons. Subtract. This becomes 103.99 newtons. Okay, so our net force in the x direction is now 222.28 newtons forward. Okay, and then last but not least again, right? So we went from normal to that x direction. Once you have the net force, remember the acceleration is just equal to now that net force that we've solved for divided by the mass of the object. So 222.28 newtons divided by our 45 kilograms is going to come out to 4.9396 newton, or sorry, meters per second squared. Okay, so you'll see that the acceleration for the push from above was equal to 2.5 meters per second squared, where the acceleration from the pull is equal to 4.9 meters per second squared. So therefore, the pull is going to be faster. Okay, and if you think about it in terms of friction, that makes sense. Remember, the only things that change friction are going to be the weight of the object changes. And that's technically what's happening here, right? Because in Newton's third law, with our floor here, the floor only exerts that force back up that is counteracting it. Okay, so in this case, because we're pushing down into the ground, the floor has to work harder, which increases the force of normal, which increases the force of friction. In the pull situation, because we're exerting an applied force up, the floor now does not have to work as hard to counteract that force of gravity. Therefore, the force of normal is smaller, which means that that force of kinetic friction is smaller, okay? And that's what gives us the greater acceleration, okay? This is Wanny signing off, and may the force be with you.